Okay, so the recording has started, and we continue on with the part 2 of course. So just quickly revisiting what we have done 2 weeks ago before the recess. We looked at electric potential, which is the energy needed to move a unit of charge from one point to another in the presence of electric field. So in order to move this charge from this point to that point, and when there is electric field, how much energy do you need to supply, or how much energy do you actually get out from it? So that's going to be the electric potential, and it's measured in volts. And if you know also the electric potential in the XYZ space, then you can also recover the electric field from the potential by taking 3 partial derivatives with respect to x, y, and z, each corresponding to x and y and z components of the electric field. So remember, the electric potential is a scalar quantity. It's just the energy required per unit charge. So it's a scalar quantity, but in order to convert this to a vector quantity, which is an electric field, you need to have, of course, you need to recover all 3 x, y, and z components in space. And electric potential due to point charges can be calculated by doing an arithmetic sum of individual contributions. So electric potential created by one charge is just going to be Ke, the Coulomb constant, times Q divided by R, meaning R is where in the space, how far away from that point charge you're trying to compute the electric potential at. Whereas if you now have multiple point charges, then you have to add contributions from multiple point charges to that point there. And if you have a continuous charge distribution, you of course have to take a integral. But remember, this is not a vector sum. This is an arithmetic sum. So in fact, computational, like calculation-wise, it will be simpler than trying to do a vector sum. And in a conductor, electric potential is always constant inside the conductor. And at the edge, just outside the conductor, it's going to be same electric potential as having a point charge in the center of the conductor. Okay, so and inside the conductor, it's going to be exactly the same across the entire inside and on the surface of the conductor. So we can make use of this to calculate a few things. And there were 2 topics that we covered 2 weeks ago. The second topic is on capacitance and dielectrics. So by having 2 conducting plates separated at certain distance d, you can create a capacitor, and capacitor can be used to store charges. And the amount of charges that can be stored in a capacitor is given by the geometry of the capacitor. But and then that capacitance also is given by the amount of charge that is stored in the plates divided by the voltage across it. Let's see. And when the capacitors are connected in parallel, the equivalent capacitance is going to be the arithmetic sum, just the normal sum of all the capacitors involved in connected in parallel. And when the capacitors are connected in series, it's going to be the inverse of the equivalent capacitance is going to be the inverse sum of all the capacitors that are connected in series. And this is how you calculate the energy stored in the capacitor. Because the capacitor, inside the capacitor, when you have these 2 charges, there's going to be electric field forming across these 2 plates, because there's a positive charge and negative charge. And eventually the energy is stored in that electric field. So you can actually consider that the electric field stores the energy, which is calculated using this way. Okay, and if you insert some dielectric medium, of the electric constant kappa, then you can actually increase the capacitance by the factor kappa. Okay, so sometimes there are some special dielectric materials that has very high kappa, like 5,000, something like that. And that means for the same geometry, you just insert that dielectric medium, and then you can increase the capacitance by 5,000 times. So that's the two topics that we have done 2 weeks ago. And if you have any questions or comments, please, now is the time. Or of course, you have other times after this too. Any comments or questions? If not, then I think we can move to magnetic fields. Okay, so I should just remind you that the second quiz, quiz 2, is going to be up to what we did before the recess. So it will cover 3 topics on electricity, and then the magnetic field, which we are doing today, and then another electromagnetism, which we will be doing next week. These are not part of the second quiz. It's not within the content covered in quiz 2. Okay? So if you are going to study for quiz 2, you should be studying those 3 topics. But of course, in your final exam, all of these will be in your final exam. All right. So when you have a magnet, magnetic field, which we use B, also exists. And B is like, it can be represented fairly similar to the electric field E. It's a vector quantity, and it's measured in Tesla with big T. And you can use magnetic field lines to visualize it, just like how you use electric field lines to visualize the electric field. And of course, then that means all the rules that we use for electric field will apply to the magnetic field lines, such as there's no crossing of 2 magnetic field lines. You always have to do a vector sum of 2 contributions, and then you'll always get just one line at certain points. And the density of the line corresponds to what? Density of the magnetic field lines would corresponds to the strength of the magnetic field. And any line tangent to this magnetic field line would be the field direction, magnetic field direction at that point, at that specific point, so that we can use it. How is the magnetic field induced? That would actually going to be the second part of today's summary lecture, which is the sources of magnetic field. But just in short summary, it is created by motion of electric charges. So if you have a moving charge, that will also create magnetic field. Okay, and we'll talk about that more later today. Okay, so when you have a moving charge and it is moving in the presence of magnetic field, that charge is going to experience some force, and that's called magnetic force. So remember when we had electric charge, when we had a electric charge, plus or minus, and when it was under the presence of electric field, it experienced force, right? And that force was the Coulomb's force. So we had to multiply the charge times the electric field. Now, similarly, when we have a moving charge in the presence of magnetic field, it will experience force, and this is given by magnetic force. And in order to calculate the magnetic force, the equation is given like this. So magnetic force is of course a vector quantity, and moving charge is also a vector quantity because it must be moving in some direction. So at some speed. So speed would be the magnitude, and direction of that movement is going to be the direction of the velocity, of course. And B is again, we talked that the magnetic field is a vector quantity. So we are actually now multiplying 2 vector quantities, and it's not a dot product, it's a cross product this time. So cross product gives you what? So before we did when we are calculating like the magnetic flux and electric flux and things like that, we were doing a dot product, which was giving us a scalar quantity after doing a dot product of the two vector quantities. Now with the cross product, we are getting another vector out of it. So this is a cross product. So this sign has a special meaning. Now I'm giving you this kind of a list of how the cross product works between unit vectors in x, y, z, the Cartesian coordinate. So if you are multiplying a unit vector in x direction and y direction, you're going to get a unit vector in z direction. If you're if you're doing a cross product between y component unit vector in y direction, z direction, you're going to get one in x direction, and so on and so forth. And if you're doing a cross product of I and j, and if you do a cross product of j and I, the resulting vector is going to be in the opposite direction. It's going to be in minus k direction or minus z direction, for instance. So this table quite useful if you're going to do a lot of cross products, because that actually gives you exact direction that you'll be getting after the cross product. Anyway, coming back to this equation, Q is the charge measured in coulombs, V is the velocity of the charge, moving charge, measured in meters per second, and B is the magnetic field strength, of course, it's measured in Tesla. And how to find out this cross direction of the cross product is you can use your right-hand rule. You can use right-hand rule, so I've drawn it here. You can put your index finger in the direction of your first vector in the cross product, and you can put your middle finger in the second vector of the cross product, and your thumb would be pointing in the direction of the resulting the result of the cross product. Okay, so in this case, you can put V on your index finger, and then B can be in the direction of your middle finger. And then FP, which is your thumb is going to be in the direction of the force. Okay. So this way you can figure out how to do your cross product, and that will help you in your solving all the problems. So you can try to use this in your questions. Of course, that's when everything is perpendicular to each other, meaning everything is 90 degrees to each other. But sometimes you don't really always get something at 90 degrees. So for instance, your moving charge may not be at a 90 degrees to the direction of the magnetic field. In that case, when you have theta here, and that's going to reduce the size of FP, and that you can use this equation, right? In this case, theta is going to be the angle between the V and B. And if you multiply all that, and then you get the magnitude of the force. And then the direction of the force is going to be perpendicular to both of these. So when you have Q and B, that's going to give you a plane. That's going to give you one plane, right? And then your force is always going to be normal to that plane. Always going to be normal to that. Okay. And when theta is 90 degrees, it should be 90 degrees there. You get the maximum because sine of 90 is 1. So you just get FB to be QVB. And when theta is 0, that means V and B are directing two are in the same direction. Then the resulting force is going to be 0 because the cross product of the two parallel vectors is 0. Okay, yeah, nothing. So now let's look at how charged particles moving in a uniform magnetic field what sort of force it will experience and how it is going to move. So when we have a particle that is moving at a constant velocity v, and if v is perpendicular to b is, in this case, I have drawn, because now we're dealing with three-dimensional space, right? Because we have to have cross product means we have to have three-dimensional space. So because we are limited to this two-dimensional slide, now we make use of something that is going into the slide or going into the page, or something that is coming out of the page. For instance, cross means something that is going into the page. So in this case, this red crosses mean the magnetic field that is going into the page. And then if I was to draw dots instead of the cross, that would mean the fields are coming out of the page. Okay, so in this case, we have B going into the page, and then Q. Let's say the Q was initially moving in this direction. Okay, now we can see that the Q, the V and B are 90 degrees to each other, because B is going in there, and then Q is moving that way. That already is 90 degrees. Okay. And so if B and B are perpendicular to each other, then particle is going to move in a circle. And how it's going to move in a circle looks like this. So when we have a velocity there, then of course, using your right-hand rule, your force is going to act in one direction, and that probably is the right direction if this Q is a positive charge, because positive charge is moving that way. You put your index finger there, and you put your middle finger into the page. How do I do that? Okay, and then you can see that the force is going to be directing towards that side, and that is going to deflect, right? That's going to deflect this charge towards where the force is. Okay, but you can kind of see that this is going to happen because your velocity is going to always be the tangential to it's going to be tangential to the, or 90 degrees to the force, and force is always going to be acting towards that way. Basically, you will end up having a circular motion of the charge with the magnetic force Fp acting as the centripetal force for the circular motion. Okay, and knowing that the centripetal force is given by mv squared or over r in your mechanics, then we can relate this to qvb, because everything is now 90 degrees, so we can remove this cross product and we just do a simple multiplication, and then we can find out what the radius of this circular motion is going to be when the charge is moving in uniform magnetic field, such as given here, or what is given here. Okay, so then that radius is going to depend on the mass and the initial velocity, of course, as well as the charge size of the charge and size of the magnetic field. Okay, and then we can calculate the period of the circular motion, how quickly it's going to circle around at what frequency, and also you can calculate the angular frequency of it, okay, using all these relations. But the entire system is easily understood if you understand that the magnetic force is going to act as a centripetal force in this circular motion of the particle under uniform magnetic field. So if so this was the case when the velocity is perpendicular to B. Okay? But of course, in general, generally speaking, the V is not going to be perpendicular. It can be at some angle. But then in that case, you can divide your V into two components. One is going to be the component that is perpendicular to B, which is going to give us the circular motion, just like here. This is the circular motion, which is the perpendicular component. And then there is also the parallel component, which is going to give us this one will not have any force, right? Because the parallel component to B, as we can see from this equation, when it's parallel or theta is 0, we get 0 force. So there will be no force acting on this particle in the horizontal direction in this case, right? There's only going to be a force acting due to the perpendicular component, which is going to give us the circular motion. But because the parallel motion, that one, there's no force acting on it. So when object has no force, what happens? There's no zero acceleration, means it will continue to travel at the same velocity without changing its velocity. So the horizontal component in this case, or the parallel component, is not going to change. It will continue to travel at the same velocity, whereas the perpendicular component is going to give us the circular motion. So it's going to move in so-called helix path, okay? Where the pitch is given, again in this case, pitch is the distance, how much it moves in one circle or in this helix path. So what you need to find out is how long it takes. So how long it takes to do one revolution, which is the period of the revolution. So you need to take this period of the revolution, and then you need to multiply that by what? You need to multiply that by the horizontal component of the velocity. Then you can find out how long this pitch is, how far each of these circular motion is going to happen when it's moving in the translational direction or in the horizontal direction. Okay, and then the radius, of course, this one has nothing to do with the parallel component, because the radius, the circular motion itself comes from the perpendicular component. So then you can simply consider only the perpendicular component and calculate the radius, just like what you did here. It's going to be exactly the same, but instead of just v, you now use v component that is perpendicular. But in this case, of course, v itself is perpendicular to b, so it's actually identical equation there. Okay. So, any questions up to this point? Or perhaps we will do this example, and then I will ask whether you have any questions or comments. Okay. Right. So let's look at this example. A beam of electrons enters a region with a magnetic field as shown below. If the beam is deflected upward, in which direction is the magnetic field oriented? So this is an electron beam. So electron beam is moving from right to left. But when electron beam is moving from right to left, in which direction is the charge Q moving? Because electrons are negatively charged, then you have to consider the polarity of your charge, and that's negative. So we can consider that this is moving from left to right, right? Because this is negatively charged particle. That means if the force is acting upwards, then in which direction is the magnetic field acting? It has to be either going into the page or coming out of the page, because we know these three: the force, magnetic field, direction, and the charge, the movement of the charge direction, they have to be all perpendicular to each other. So if this is 90 degrees, then it has to be again another one that is perpendicular, which is the magnetic field. It either has to go into the page or coming out of the page, right? And in this case, it has to be going into the page, because only if you place your middle finger going into the page and your the index finger going into the right direction, then you can have force moving upwards with your thumb. So using that, you can figure out that B must be directed into the page. Okay, so that's how you get it. So you should try to practice this quite often when you solve example questions. Okay. Any questions up to this point? Okay, so I will continue. So what if we have both electric field and magnetic field in the system? Then you have a charge, you have a charged particle, and it will be experiencing both the the electric force, which is due to the electric field, as well as the magnetic force, which is due to the magnetic field. And we know that the electric field is given by QE, and magnetic field is given by QV cross B. And the total force is going to be, of course, the electric force plus magnetic force, and it's going to be a vector sum because these are all vector quantities. So then we can get the total force using this relation, right? So this is called Lorentz force. So let's look at another example where we have both electric field and magnetic field. So we have a negative charged particle, and that's in between the two plates of a capacitor. So this side we have negative charge, this side we have positive charge. So in which direction is the electric field flowing? The electric field due to these two plates is directed from right to left. Is that correct? Yes. Directed from right to left, so that's E. And then under the combined influence of magnetic field B, so B is these red dots. So when we have red dots, it's directed out of page. So that's directed out of page. It's coming out of the page. And the electric field in the capacitor, which of the paths shown best represents the trajectory of the particle? So we need to ignore the gravity. So it says the charged particle is released from rest. So it's not moving initially. So when it's not moving, do we have any magnetic field? Do we have any magnetic force acting on the particle? No, because when it is at rest, V is 0. So that thing is going to be 0. The magnetic force is going to be 0. But we still have the electric force, because electric force doesn't require the charge to move. We just need to have a charge under the influence of the electric field. And because electric field is moving that way and this is negatively charged, which way is this going to, in which direction is this electric force going to be? It's going to be towards the right. So this yellow line represents the initial force acting on the rest particle, on the rest negatively charged particle. Now, as it starts moving, what happens? Now it gains velocity, right? Now it's a moving charge. So what you're going to have is some magnetic force acting on the charge because it's moving. So in which direction is that force going to be? Now the velocity is going to be this way, but because it's a negatively charged, you have to put your index finger in which direction? To the left. You put your index finger to the left, and then your middle finger must be pointing out of the page, directed out of the page, and your force is going to, your thumb is going to move upwards. So this green arrow represents the QV cross B in this case. Okay, the QV. So V, in fact, is this. V is this way, but because Q is negative, that's going to, the QV is going to be directed that way, towards the left, and B is pointing towards us or coming out of the page, and then cross product of the two is going to give us a direction towards upwards. Okay, in this case. So out of these paths that I have drawn in, I think number 3 represents the best how the particle is going to move, because initially it will not have any force acting in the vertical direction, but it will start to gain the vertical direction, force in the vertical direction, because we start to have some speed, movement of the charge starting from the rest. Okay, number 2 is not quite right, because this has some vertical component from the very beginning, which is not quite true in this case because it was starting at rest. And all the others seems not so correct. Okay. So I hope you fully understood how we got to the solution of the past number 3. Right. So any questions up to this point? Okay. So since moving charge was subject to force when it was under the influence of magnetic field, then if you have a current carrying wire, current carrying wire means there's continuous flow of charges, right? It's continuous flow of charges. If you have a current carrying wire and you place it under magnetic field, and it's going to also experience some force, magnetic force, right? And then that magnetic force is given by I and L cross B, where L direction of L is in the direction of pointing in the direction of the current flow, and I is the size of the current, and B is of course the magnetic field, and then you can get your magnetic force FB like that. Okay, if you do a unit analysis of this equation, it is actually same as there's the same unit as where is this one? Okay, because I is current, and current is measured in what? The current is measured in coulombs per second. Okay, coulombs per second. What that means is I. So 1 ampere means there is 1 coulomb of current. 1 coulomb of charge that is passing through this particular section of the wire per second. Okay, that's exactly what it means. And so if you do this, then that will give you same as coulomb, the charge times the velocity, which is charge times meter per second, and then this is actually charge per second times meter, right? So that gives you the same unit, and eventually you will have the same unit if you do this calculation. I think I've written it down there. Again, this turns into a simple multiplication if L and B are, if the vector L is actually directed towards the direction of the current, and vector L and B are 90 degrees, it will just turn into a simple multiplication. But if it's at an angle, theta, then you have to do this calculation because it's a cross product. So that was, this is for a straight wire. This equation is for current carrying wire that is straight, but your wire may not be always straight, of course. It can be a curved wire like that. And in that case, what you need to do is you need to consider a very little element. So you need to consider the force due to very little elements of ds. Okay, and then you need to add them all together. Basically, that means you need to do an integration over the entire length of the wire that is under the influence of the magnetic field. And so yeah, by calculating a little contribution from little sections of the wire like that. Okay, and then that will be your force acting on the wire. But in fact, if you look at that, it will actually be same as doing the same. It will be same as doing a calculation on assuming that the wire is a straight line from A to B. So you just draw a straight line from A to B, and then if you calculate the force acting on this this imaginary line, let's say imaginary line, then that's going to be same as actually doing all the calculations of this curved path. And that's because it's when you do the vector sum, all these, when it's going up, right, there's going to be certain component that gets cancelled out down here. Okay, So when you draw a straight line through, all the components that is moving above or below that straight line is going to get cancelled out because if we are under the uniform B, of course, if the B is changing from here to there, then that's not going to be quite true. But if we are under uniform B, then we can assume that we can draw a straight line from A to B, and then we can draw an arbitrary, or not arbitrary, imaginary wire from A to B, and we can do the calculation in this simple manner, rather than trying to do all this integration. So it says FB on a curved wire is equal to actually FB on a straight wire between the two ends of the curved wire. So that simplifies our problem. And then that actually gets us to that if we have a closed loop wire, if we have a totally closed loop wire, then obviously then this we will not be able to draw any L, right? Because A and B are now the same point in a closed wire, like that. And that's going to give us absolutely no force. It's going to give us zero force. So in a closed, if a closed wire and there is a current flowing I, and it's placed inside a magnetic field B, a uniform magnetic field B, there's going to be zero force acting on it. Force. Okay, so any questions up to this point? So I will do a quick summary of this on this topic. So we've talked about what magnetic field is. So when we have a magnet, then you can there's going to be a field around the magnet where the field line will start from the north pole and then it will end at the south pole. You can draw a field line like this, just like how you draw electric field lines. And when there is a moving charge inside magnetic field, then it will experience force, and this is called magnetic force. And you can calculate the magnetic force using this equation. And in order to determine in which direction the magnetic force is acting, you need to use your right hand rule to figure this out. So do remember how to learn how to use the right hand rule. And if the magnetic force is acting on a charged particle, it can move in a circular motion like that. And if the velocity is not fully perpendicular to the field, magnetic field, then it will be moving in a helix path. So it's moving in a circle, but with some translational motion. And because current carrying wire means there are moving charges inside the wire, it will also, if we place this under magnetic field, and it will also experience some magnetic force acting in this relation. That's the summary of the first part of today's lecture. So the second part, we're going to talk about the sources of magnetic field. So where does this magnetic field come from? So electric current creates magnetic field that curls around it. So when you have moving charges, it actually creates its own magnetic field. Okay. So when the current is flowing in some direction on a straight wire, around it curls around. Around it will create magnetic field. And the direction of the magnetic field is you can use so-called right-hand grip rule. So you put your you have your right hand, and then put your thumb in the direction of flow of the current, and then how your finger curls around your thumb is going to be in the direction of, is going to give you the direction of the magnetic field. So this is called right-hand grip rule. So for instance, in this case, this is a current carrying wire. Then if you put your right hand around it, put your right hand grip around it, then you can see that your fingers are going to come out of the page on the top of the wire, whereas in the at the bottom of the wire, it's going to go into the page, right? Because if you put your fingers around it and then put your thumb in this direction, that's how the direction of the magnetic field is going to be. Okay. Now, in order to calculate the magnetic field at point P, then what you need to do, due to the current carrying wire from here to, which extends from here to there, then what you have to do is you need to calculate the contributions of every little small pieces of the wire at that point, and then add them all up. And this is, of course, will lead you to this integration. Okay. So that ds is going to be the very little components along the length of the wire, and that r squared is the distance from how far you are at that little section to the point P that you're trying to calculate that magnetic field. So that what that says is that if you are very close to the wire, the contribution of that part is going to be very strong. Whereas if you are far away, the contribution is going to be very small, because r square, its dependence is the inverse of the r square. Okay. And then again, this cross product gives you the direction. So that's why the cross product between ds and r is going to give you something that is coming out of the page on this side, and then something that is going into the page on the other side. That's the result of this cross product. So this is for a curved current carrying wire. If you have a straight wire, like that, then it simplifies to this equation. So if you do actually take the integral, and it simplifies to this equation, where θ1 is from point P to one end of the wire, and θ2 is from point P to the other end of the wire, the angle that created by that. Okay. So if you have an infinitely long wire, that means θ1 is going to be what? If this is infinitely long, that angle is going to reduce, and it will eventually become 0, right? So that part is going to be 1, because cosine of 0 is 1. And then if it's infinitely long, then θ2 is going to increase and increase and increase until, when it's infinitely long, what will happen to θ2 is going to become 180 degrees, right? So when you have cosine of 180 degrees, that's -1. So this entire thing becomes 1 minus -1, which is 2. So you multiply 2 there, and then you get this. So this is the magnetic field for an infinitely long wire, and it simply depends on what? It simply depends on how much current the wire is carrying and how far you are actually from that wire. The exact derivation of this equation, which led to this one, is actually given in the lecture note. So if you want to find out how to do that, you can take a closer look at the actual lecture note, the summary lecture. Okay. All right. So we talked about how having an electric current flow creates the magnetic field. And similarly, when we have current flowing in a circle, so if the current flow is a curve, that means it's flowing in a circle, then this also creates what? It creates a magnetic field in a straight direction. Well, it's not really straight, but and you can use the same right-hand grip rule. So you can place your fingers around the direction of the current flow, and then your thumb is going to be in the direction of the magnetic field. Okay. So in this case, if we have a current flowing in this circular direction, then this is going to be the North Pole, and that's going to be the South Pole of our magnet. So we can create a magnet like that. Okay. So coming back here, 2 ways. One is you have a current flowing straight through, and then we create a magnetic field that is circles around the direction of the current flow. And if we have a current flow that is in circle, then we have a magnetic field that goes straight through that circle current flow, circular current flow. That's I hope you can understand the symmetry of the whole thing. The symmetry of it. Right, so let's take a look at this example. So we have two positive charges moving towards the origin, as shown here. So that one is moving along the y-axis. This one is moving along the x-axis. At the instance shown, at this instance, in which direction is the magnetic force of Q2 on Q1? Okay, so what does that mean? Q2 is moving this way, and that's a current moving in that way, right? And in which direction is the magnetic field going to be created due to Q2? Then you need to do a right-hand grip rule, and you place your thumb in the direction of the Q2, and then you put your fingers around it, wrap around it, and that will give you magnetic field coming out of the page on the negative y side and going into the page in the positive y side. And that is due to Q2, of course. So when there is a magnetic field that is going into the page on the positive y side, then we can actually see that there's going to be a force acting on Q1 due to that magnetic field. And the magnetic force acting on Q1 due to that presence of the magnetic field here now, right? And that is going to, you need to use the right hand rule to place your index finger on the direction of V1 because this is positive charge, and place your middle finger going into the page, and your thumb is going to be directing towards the positive x side. Okay? So then you can solve this problem. Any questions on this point? If you have any questions or comments, please let me know. Okay, I will continue. So we're going to take a look at Ampere's law. So we learned that when we have current carrying wire, it's going to have magnetic field around it. Okay. So for instance, this one. Let's forget all the other I's. Let's forget all the other I's. When we have I1, this is coming out of the page. So which way, in which direction is this going to be? Is the magnetic field due to I1 going to be? Put your thumb coming out of the page, and then you put your finger wrapping around it with your right hand. Don't use your left hand. Okay. Then it's going to be in the counterclockwise direction, right? It's going to be in the counterclockwise direction around I1. And I2 is going to be, you could put your thumb into the page, and then you put your fingers wrap around it. And that's going to be in the clockwise direction. And again, this is also going to be in the clockwise direction. And of course, we can continue to draw our magnetic field around it like that. But of course, because we cannot have magnetic field lines crossing, it's going to create some sort of vector sum. And we should be able to draw in all the magnetic field lines due to these current carrying wires just around it like that, okay? Including I4, of course. But what Ampere's law says is that if we calculate the magnetic field around a closed loop like that, so if we do a line integral of the magnetic field around any closed loop, then that integral is going to be proportional to the total current that is enclosed inside the loop. Okay, so in this case, if I do a line integral of this arbitrary closed loop, this is an arbitrary closed loop of all the, so let's say B is going to be due to all of these, and then of course I need to do a small contribution, a small ds contribution, add them all together at every point along this closed loop line. Then that's going to be mu naught times I1, because I1 is positive because it's coming out of the page. I just give any, in this case, I am defining something that is coming out of the page to be positive and something that is going into the page to be negative. So I1 minus I2 and minus I3. So that net current is going to be this one. So that net steady current is going to be proportional to the line integral around this Amperian, this is called Amperian loop. And in this case, of course, I4 is outside this closed Amperian loop, and that we can ignore in our calculation. So in fact, this infinitely long current carrying wire, if you remember, this was the equation for it, which we got it from here. So now assume that this is infinitely long current carrying wire that is coming out of the page, for instance, in this case. So imagine that is I1, that current carrying wire, and then you don't have any I2, I3, or I4, and then you put a circle around it, just like that. Okay, circle around it. Then if you use this relation, the closed loop circle is going to give you 2 pi r, right? It's going to give you 2 pi r, and then you can see that it's going to give you a mu zero, the permeability of the free space, times I divided by 2 pi r. So you can actually get B due to an infinitely long current carrying wire using this Ampere's law, or you can also use this equation and do the integration to get this equation. So either way you do it, you get the same results. That's the point. Okay. So now the next part, we're going to look at Gauss's law in magnetism. So if you remember what Gauss's law in electricity is, remember that? It was, if you have a Gaussian surface, what's a Gaussian surface? It's a closed surface, right? It's a closed surface which contains some volume inside, right? So if you have a Gaussian surface, the total net flux through these Gaussian surface is going to be proportional to the net charge enclosed in that volume enclosed by the Gaussian surface. That was Gauss's law in electricity, or we just call it Gauss's law. And similarly, we have also Gauss's law in magnetism. Okay, and we're going to look at how this Gauss's law in magnetism work. Before we do that, because you remember electric field, the Gauss's law in electricity, that we had to come up with the concept of electric flux, right? But likewise, we also need to understand what magnetic flux is, and it's actually exactly the same concept. So remember, we were able to draw the magnetic field lines, and B was proportional to, so the number of magnetic field line, the density of the magnetic field line was proportional to the magnetic field strength B. So magnetic flux, what magnetic flux is the actual number of magnetic field lines that is passing through a surface. So I'm using exactly the same picture as when we first introduced the electric flux, but I just changed B to, it was E before, now it's B. So in this case, the magnetic flux through this surface, this magenta highlighted surface, is going to be same as the magnetic flux that is passing through this green highlighted the area. Okay, and it is actually, magnetic flux denotes the number of magnetic field lines that's passing through a surface. Okay, And the unit for magnetic flux, the symbol for magnetic flux is the capital phi with B meaning the magnetic flux. And if it was electric flux, it was the capital phi with subscript E. And it's given by B times A, where A is the area of the surface. And then this cosine theta, of course, tells that it should be at an angle. Okay, theta gives you the angle. So when theta is 0, meaning the field line and then the surface area is at a 90 degrees to each other, because the surface area vector is always normal to the actual plane, the surface plane. Okay, so when theta is 0, then you get the maximum flux, and when theta is 90, you get 0 flux. Okay, so that's why we use cosine theta here. So that gives you so the magnetic flux is going to be the dot product between the field B, the field vector V, the magnetic field vector V, and the area vector A. Okay, and the unit for this is going to be Tesla meter squared, meaning because that's Tesla for the magnetic field, and meter squared is coming from the area, and it's also called Weber, which is the short form is WB, and 1 Tesla meter squared is equivalent to 1 Weber. I was just introducing magnetic flux so that we can talk about the Gauss's law in magnetism. And now coming back to electric, the Gauss's law in electricity, it was that the total net flux through the Gaussian surface is proportional to the charge enclosed in that charge enclosed in that surface. Now in magnetism, actually the total net flux through a Gaussian surface, or total magnetic net flux through any Gaussian surface, is going to be 0. So there's no that. Why is that? Because there's no net magnetic charge that can be non-zero. There's no non-zero net magnetic charge possible, because you can have separate positive charges and negative charges. You can separate them, and then you can just have net positive charge here, and you can have just net negative charge here. But with the magnetic poles, which is north and south pole, you cannot separate them out. Okay, they always come in pairs. So for instance, if you have a magnet and one side is positive and the other side is negative, of course. No, positive, sorry. One side is north and the other side is south. If you cut it, then what happens? Do you just get north and south separated out? No. What happens is that when you cut them, then this half will have north and south of its own. Then the other half will have north and south of its own. So you can never separate them out. They always come in pair. That means it is impossible to have any net north or south poles inside any enclosed, finite enclosed surface. Okay, that's why it will always be 0. So even if you have any magnets here, because it will have both south and north, the total net flux through the Gaussian surface is always going to give you 0. So for instance, in this case, what this tells us is that all lines that goes into the Gaussian surface must come out somehow at one point. So the total number of magnetic field lines that is going into this Gaussian surface is going to equal the total number of lines that's coming out of the surface, the Gaussian surface. That's the Gauss's law in magnetism, and that leads us to this equation. So do you fully understand this equation now, that this is the total net flux through a closed surface, and that is 0. Okay, so this probably is the last. This is probably the last law that we're going to look at in today's summary lecture, is Ampere-Maxwell's law. So if you remember, we had the Ampere's law, which told us what? In any, if we do a line integral of any closed loop, we do a line integral of any closed loop, which was this one. We do a line integral of any Amperian loop or closed loop, then it will be proportional. The integral will be proportional to the total net steady state, steady current. It will be proportional to the net steady current that is enclosed inside that Amperian loop. Okay, and this is only valid for when I is steady. What is I steady mean? When I doesn't change with time. Okay, when I changes with time, this doesn't work. Okay, so this is only valid for DC current. So if that current is always the same. But if the current changes, for instance, in alternating current, you know, in alternating current, the current is going up and down and up and down and up and down like that. You also need to include an additional term, and this term, so this was work of Maxwell, a scientist called Maxwell. So Ampere came up with this Ampere's law, but then Maxwell realized that this only works when I is DC, and when there is AC, something that changes with time, then there must be some additional term that must, you know, that must count for take this into account. Okay, and this is so-called displacement current. Okay, so instead of just having mu 0 I, you have to do mu 0 and I plus the displacement current. And this displacement current is in fact the time varying term. That means it changes with time, and that's where this AC is coming from. Okay, so what this says is that both conduction currents, meaning something that is steady state, and some time varying electric field is going to create magnetic field. So it is possible to create magnetic field not just with some steady state current, which we use our right-hand grip rule and so on to compute. Also, a time varying electric field is going to create magnetic fields. That's the meaning of this additional term. Okay. So if we had an Amperian loop like that, so that's again, this is the closed loop line integral. So when we do a line integral of this Amperian loop, then this, if there is an electric field going through this Amperian loop, and if it changes with time, that's also going to create non-zero magnetic field. That's what this is saying. So there is one example that describes this Ampere-Maxwell law, which is given in the last page. Is it last 2 pages? I think. So this one a little bit long. So if you don't fully follow it, please take your time to take a look at the lecture notes very carefully. And if you still have questions or need to clarify points, then you can always try to contact me or your tutor also. So let's look at this question, this example. We have a capacitor below and has a circular plates of radius r. So these are 2 plates capacitor, 2 parallel plate capacitor, separated, I suppose, by d. And then we have points A, P, and B, Q. All right. So 2 points A and P are outside the capacitor. It's near the wire. In the wired section, whereas BQ are inside the capacitor, so there's no current there. Okay, and the location of A is r away, distance r away from the wire, and then P is distance half r away from the wire, and likewise Q is distance half r away from the center of the plate, and B is distance r away from the center of the plate. And now we need to rank the the strengths of the magnetic field at these 4 points. Ranking means which one has the strongest magnetic field and which one has the weakest magnetic field and so on. So let's take a look at how we can solve this. So that's the solution. So the easier part is this part where we have the wire, because we can easily calculate the magnetic field at A and P using this equation, which we got it from the Biot-Savart law in this one, right? This one we already have. Of course, it's not infinitely long, but we can assume that the wire is very long. In many of these examples, we need to assume a lot of things. And here, let's assume that this is very, very long and is much, much longer than this far away. Then we can say the magnetic field at A is going to be mu naught I divided by 2 pi r, where r is that distance, right? And because at P, r is half only, and that means we can just remove that 2, and then that's going to be this. So you can kind of see that BP is going to be much stronger than BA, because it's going to be not much. I mean, it's going to be 2 times stronger than BA. So that's that. Now, a bit more difficult part is calculating this BQ here, right? So in order to do this, so okay, let me just come back to this one first. So at this point here, which of these two did we use? Which of these two did we use? We used the steady term only, because in this part, there's no time varying term. There's no time varying term. There's only the steady current, because the current is just flowing steadily with I. Okay. There's no time varying term and there's a steady term. So when we do a line integral around the circle with the radius half r or radius r, then when we do the line integral, we're going to get 2 pi r and we're going to get pi r, right? So because this is half r, then the line integral of that circle is going to be circle that includes the P, point P, is going to be, in this case, pi r, and then this is going to be 2 pi r. So using that, we can, substituting that substituting that into here, it's going to be 2 pi r b is equal to mu naught I. So then that gives us the B is equal to mu naught I over 2 pi r. Okay? And that's for, of course, at point A, and for point B, that's going to be just pi r, because that's what the radius, what the circumference of that, the line integral of that is going to be. That includes the point P. Now, at point P, B and Q, at point B and Q, do we have any steady current there? You don't have any steady current because there's no current carrying wire there. There's only the time varying term. Okay, there's only going to be a time varying term. So we cannot use this one, but we have to use, this is going to be 0. This steady term contribution is going to be 0 between the capacitor plates. And we're going to just need to use that part. Okay. Again, we create our Amperian loop around that includes point Q, a circle, and B also another Amperian loop. So that means it's going to be 2 pi r B for that Amperian loop, which is the outer Amperian loop, and for the inner Amperian loop, it's going to be pi r B. So just rearranging it, then we get that, and this mu naught and epsilon 0, this is the electric flux that is going through this Amperian loop, because we can use it from this equation. That is the flux going through that Amperian loop. And that is the time varying flux that is going through the Amperian loop. So we can use, we can attach that here, and then that is going to give us the time varying contribution to this magnetic field at B and BQ. Okay, Is that are you able to follow this? Okay. So this magnetic flux, of course, the electric field is, in this way, and that's at 90 degrees to this area there, all of these two areas. So then we can simply calculate the electric field times the area of the circle that we have drawn, or the area of the Ampérian loop, the area that is covered by the Ampérian loop. So that's going to be pi r squared in this case when we have B. And for Q, because that r is only half r, then the radius is only half r, then it becomes that part. Okay. And then we can simplify the whole thing, and then we get that. So now we are left with this part where we have a time varying electric field. So what does that say is, how does this electric field vary with time? Okay. Now that, in order to get that, we need to understand that this E times D, which is electric field times the distance between these two plates, is going to give us the potential difference between these two plates. And from the definition of capacitance, which was Q divided by the potential difference delta V, then we can substitute this N. And again, the capacitance is given by for capacitance for two parallel plates is given by epsilon 0 times area divided by D. We know that. So area is, again, of this capacitor is pi r squared, and then divided by D. So I'm substituting this C with epsilon 0 pi r squared over D, and then I get this. And when we rearrange the whole thing, we can find out that E, electric field, is going to be Q, which is the charge on the plate, divided by epsilon 0 pi r squared. So I can substitute this into these two expressions. Then I can do a lot of simplification, I think, cancellation, epsilon 0, and so on and so forth. Then I can get BB to be mu 0, the permeability of free space, divided by 2 pi r. And then this is the rate at which this part, the plate, is charged. Okay, this dq over dt is the rate at the rate of the plates being charged. And that dq over dt, in fact, is going to be the current that it flows into the plate, because I, again, is, as we have described, it's given in coulombs per second, is the rate at which the charge flows through a certain point. So that charge flowing in at this point is going to actually end up here, right? And it's going to charge this plate up. So then we can replace dq over dt by I, and then we eventually end up having dB of this and bq of this expression. And then we can rank them from the smallest to the next, and then to the largest, this way. So I hope you were able to follow this. If you did find it difficult, do take time for you to digest slowly. And if you need further assistance, please do let me know, or your tutors. So I'm going to give a quick summary of what we have done in the second part of this summary lecture. So flow of electric current will create magnetic field. Okay. Electric field, current electric current flow is going to create a magnetic field that curls around the direction of the electric flow. And what Ampere's law states is that the line integral of the magnetic field around an Amperian loop, a closed loop, is going to be proportional to the total steady current that is enclosed inside the Amperian loop. And Gauss's law in magnetism says that we cannot have any separation of north and south pole, so such that the total net magnetic flux through a Gaussian surface is always going to be 0. And then Amperian Maxwell law, Maxwell actually added the time varying component that depends on how the electric flux through the imperial loop changes with time also contribute to the creation of the magnetic field around it. So that finishes our summary lecture today. So thank you for attending the class. And if you have any questions, please do remain and write your questions here, or unmute yourself and ask. Otherwise, I will see you next week. Thank you, Yuha.